At the dawn of the 19th century, in a cellar in Mayfair, the most famous scientist of the time, Humphrey Davy, built an extraordinary piece of electrical equipment. 4 meters wide, twice as long, and containing stinking stacks of acid and metal. It had been created to pump out more electricity than had ever been possible before. It was, in fact, the biggest battery the world had ever seen. And with it, Davy was about to propel us into a new age. That moment would take place at a lecture at the Royal Institution in front of hundreds of London's great and good. Filled with anticipation, they packed the seats, hoping to witness a new and exciting electrical wonder. But what they would see that night would be something truly unique, something they'd remember for the rest of their lives. Using just 2 simple carbon rods, Humphrey Davy was about to unleash the true potential of electricity. Electricity is one of nature's most awesome phenomena, and the most powerful manifestation of it we ever see is lightning. This is the story of how we first dreamed of controlling this primal force of nature, and how we would ultimately become its master. It's a 300-year tale of dazzling leaps of imagination and extraordinary experiments.
Tens of thousands of volts passed across his body and through the end of a lamp that he was holding.
It's a story of maverick geniuses who used electricity to light our cities, to communicate across the seas and through the air, to create modern industry, and to give us the digital revolution. But in this film, we'll tell the story of the very first scientists who started to unlock the mysteries of electricity. There's something alive in there. They studied its curious link to life, built strange and powerful instruments to create it, and even tamed lightning itself. It was these men who truly laid the foundations of the modern world. And it all started with a spark. Imagine our world without electricity. It will be dark, cold, and quiet. In many ways, it will be like the beginning of the 18th century, where our story begins. This is the Royal Society in London. In the early 1700s, after years in the wilderness, Isaac Newton finally took control of it after the death of his arch-enemy, Robert Hooke. Newton brought in his own people to the key jobs to help shore up his new position. The new head of demonstrations there was 35-year-old Francis Hawksby. Notes from the Royal Society in 1705 reveal how hard Hawksby tried to stamp his personality on its weekly meetings, producing ever more spectacular experiments to impress his masters. In November, he came up with this, a rotating glass sphere. He was able to remove the air from inside it using a new machine, the air pump. On his machine, a handle allowed him to spin the sphere. One by one, the candles in the room were put out. And Francis placed his hand against the sphere. The audience were about to see something amazing. Inside the glass sphere, a strange ethereal light began to form, dancing around his hand. A light no one had ever seen before.
Oh, that's fantastic. You see a beautiful blue glow. It's just marking out the shape of my hands, but then going right round the ball. It's as though there's something alive in there.
It's difficult to really understand why this dancing blue light meant so much. But we have to bear in mind that at the time, natural phenomena like this were seen to be the work of the Almighty.
This was still a period when, even in Isaac Newton's theory, God was constantly intervening in the conduct of the world. And so it made sense for a lot of people to interpret natural phenomena as acts of God.
So when a mere mortal meddled with God's work, it was almost beyond rational comprehension.
Hawksby never realised the full significance of his experiment. He lost interest in his glowing sphere and spent the last few years of his life building ever more spectacular experiments for Isaac Newton to test his other theories. He never realised that he'd unwittingly started an electrical revolution.
Before Hawksby, electricity had been merely a curiosity. The ancient Greeks rubbed amber, which they called electron, to get small shocks. And even Queen Elizabeth I marvelled at static electricity's power to lift feathers. But now, Hawksby's machine could make electricity at the turn of a handle, and you could see it. And perhaps even more importantly, his invention coincided with the birth of a new movement sweeping across Europe, called the Enlightenment. Enlightened intellectuals used reason to question the world, and their legacy was radical politics, iconoclastic art, and natural philosophy, or science. But ironically, Hawksby's new machine wasn't immediately embraced by most of these intellectuals, but instead by conjurers and street magicians. And those with an interest in electricity called themselves electricians.
One story tells of a dinner party attended by an Austrian count. The electrician had placed some feathers on the table and then charged up a glass rod with a silk handkerchief. He then astonished the guests by lifting up the feathers with the rod.
He then went on to charge himself up using one of Hawksby's electrical machines and gave the guests electric shocks, presumably to squeals of delight. But for his pièce de résistance,
He placed a glass of cognac in the centre of the table, charged himself up again, and lit it with a spark from the tip of his finger.
There was a trick called the electrical beatification, in which the victim sits on an insulated chair, and above his head hangs a metal crown that doesn't quite touch his head. And then if the crown is electrified, then you get an electric discharge around the crown that looks exactly like a halo, which is why it's called the electric beatification.
as England and the rest of Europe went electricity crazy, the spectacles grew bigger. And the more curious electricians started to ask more profound questions. Not only how can we make our shows bigger and better, but how can we control this amazing power? And for some, can this incredible electrical fire do more than just entertain? One of the first early breakthroughs would never have happened had it not been for a terrible accident.
This is Charterhouse in the centre of London. Over the past 400 years, it's been a charitable home for young orphans and elderly gentlemen. And sometime in the 1720s, it also became home to one Stephen Gray. Stephen Gray had been a successful silk dyer from Canterbury. He was used to seeing electric sparks leap from the silk, and they fascinated him. Unfortunately, a crippling accident ended his career and left him destitute. But then he was offered a new life here at Charterhouse, and with it, the time to perform his own electrical experiments.
Here at Charterhouse, possibly in this very room, the Great Chamber, Stephen Gray built a wooden frame. From the top beam, he suspended 2 swings using silk rope. He also had a device like this, a Hawksby machine, for generating static electricity. Now, with a large audience in attendance, he got one of the orphan boys who lived here at Charterhouse to lie across the 2 swings.
Gray placed some gold leaf in front of him. He then generated electricity and charged the boy through a connecting rod. Gold leaf, even feathers, leapt to the boy's fingers. Some of the audience claimed they could even see sparks flying out from his fingertips. Show business indeed. But to the curious and inquiring mind of Stephen Gray, this said something else as well. Electricity could move. From the machine to the boy's body, through to his hands. But the silk rope stopped it dead. It meant the mysterious electrical fluid could flow through some things, but not through others.
It led Gray to divide the world into 2 different kinds of substances.
He called them insulators and conductors. Insulators held electric charge within them and wouldn't let it move, like the silk, or hair, glass, and resin, whereas conductors allowed electricity to flow through them, like the buoy, or metals. It's a distinction which is still crucial even today. Just think of these electric pylons. They work on the same principle that Gray deduced nearly 300 years ago. The wires are conductors. The glass and ceramic objects between the wire and the metal of the pylon are insulators that stop the electricity leaking from the wires into the pylon and down to the earth. They're just like the silk ropes in Gray's experiment. Back in the 1730s, Gray's experiment may have astounded all who saw it, but it had a frustrating drawback. Try as he might, Gray couldn't contain the electricity he was generating for long. It leapt from the machine to the buoy and was quickly gone. The next step in our story came when we learnt how to store electricity. But that would take place not in Britain, but across the Channel in mainland Europe.
Across the Channel, electricians were just as busy as their British counterparts, and one centre for electrical research was here in Leiden, Holland. And it was here that a professor came up with an invention that many still regard as the most significant of the 18th century, one that, in some form or another, can still be found in almost every electrical device today.
That professor was Pieter van Musschenbroek. Unlike Hawksby and Gray, Musschenbroek was born into academia. But ironically enough, his breakthrough came not because of his rigorous science, but because of a simple human mistake.
He was trying to find a way to store electrical charge ready for his demonstrations. And you can almost hear his train of thought as he tries to figure this out. If electricity is a fluid that flows a bit like water, then maybe you can store it in the same way that you can store water.
So Musschenbroek went to his laboratory to try to make a device to store electricity. Musschenbroek started to think literally. He took a glass jar and poured in some water. He then placed inside it a length of conducting wire, which was connected at the top to a Hawksby electric machine. Then he put the jar on an insulator to help keep the charge in the jar. He then tried to pour the electricity into the jar, produced by the machine, via the wire, down through into the water. But whatever he tried, the charge just wouldn't stay in the jar. Then one day, by accident, he forgot to put the jar on the insulator, but charged it instead while it was still in his hand. Finally, holding the jar with one hand, he touched the top with the other and received such a powerful electric shock he was almost thrown to the ground. He writes, "It's a new but terrible experiment which I advise you never to try. Nor would I, who've experienced it and survived by the grace of God, do it again for all the Kingdom of France." So I'm going to heed his advice, not touch the top, but instead see if I can get a spark off of it. The sheer power of the electricity which flew from the jar was greater than any seen before. And even more surprisingly, the jar could store that electricity for hours, even days. So in honor of the city where Musschenbroek made his discovery, they called it the Leyden jar. And its fame swept across the world.
And very rapidly from 1745 through the rest of the 1740s, the news of this, it's called the Leyden jar, goes global. It spreads from Japan in East Asia to Philadelphia in Eastern America. It became one of the first quick, globalized scientific news items.
But although the Leyden jar became a global electrical phenomenon, no one had the slightest idea how it worked.
You have a jar of electric fluid, and it turns out that you get a bigger shock from the jar if you allow the electric fluid to drain away to the earth. Why is the shock bigger if the jar's leaking? Why isn't the shock bigger if you make sure that all the electric fluid stays inside the jar? That was how mid-18th century electrical philosophers were faced with this challenge.
Electricity was without doubt a fantastical wonder. It could shock and spark. It could now be stored and moved around. Yet what electricity was, how it worked, and why it did all these things was nothing less than a complete mystery. Within 10 years, a new breakthrough was to come from an unexpected quarter. From a man politically and philosophically at war with the London establishment. And even more shockingly for the British electrical elite, that man was merely a colonial, an American. This painting of Benjamin Franklin hangs here at the Royal Society in London. Franklin was a passionate supporter of American emancipation and saw the pursuit of rational science, and particularly electricity, as a way of rolling back ignorance, false idols, and ultimately his intellectually elitist colonial masters.
And this is mixed with a profoundly egalitarian democratic idea that Franklin and his allies have, which is this is a phenomenon open to everyone. Here's something that the elite doesn't really understand, and we might be able to understand it. Here's something that the elite can't really control, but we might be able to control. And here's something above all, which is the source of superstition. And we, rational, egalitarian, potentially democratic intellectuals, we will be able to reason it out without appearing to be the slaves of magic or mystery.
So Franklin decided to use the power of reason to rationally explain what many considered a magical phenomenon: lightning. This is probably one of the most famous scientific images of the 18th century. It shows Benjamin Franklin, the heroic scientist, flying a kite in a storm, proving that lightning is electrical. But although Franklin proposed this experiment, he almost certainly never performed it.
Much more likely is that his most significant experiment was another one, which he proposed but didn't even conduct. In fact, it didn't even happen in America. It took place here in a small village north of Paris called Marly-le-Ville.
The French adored Franklin, especially his anti-British politics, and they took it upon themselves to perform his other lightning experiments without him. I've come to the very spot where that experiment took place.
In May 1752, Georges-Louis Leclerc, known across France as the Comte de Buffon, and his friend Thomas-Francois Delibar erected a 40-foot metal pole, more than twice as high as this one, held in place by 3 wooden staves just outside Delibar's house here in Marly-le-Ville. The metal pole rested at the bottom inside an empty wine bottle.
Franklin's big idea had been that the long pole would capture the lightning, pass it down the metal rod, and store it in the wine bottle at the base, which worked as a Leyden jar. Then he could confirm what lightning actually was. All his French followers had to do was wait for a storm. And then on May 23rd, the heavens opened.
At 12:20, a loud thunderclap was heard as lightning hit the top of the pole. An assistant ran to the bottle. A spark leapt across between the metal and his finger with a loud crack and a sulphurous smell, burning his hand.
The spark revealed lightning for what it really was. It was the same as the electricity made by man.
It's hard to overestimate the significance of this moment. Nature had been mastered. Not only that, but the wrath of God itself had been brought under the control of mankind. It was a kind of heresy.
Franklin's experiment was very important because it showed that lightning storms produce or are produced by electricity, and that you can bring this electricity down. That electricity is a force of nature that's waiting out there to be tapped.
Next, Franklin turned his rational mind to another question. Why the Leyden jar made the biggest sparks when it was held in the hand? Why didn't all the electricity just drain away? And drawing on his experience as a successful businessman, he saw something no one else had. That, like money in a bank, electricity can be in credit, what he called positive, or debit, negative.
For him, the problem of the Leyden jar is a problem of accountancy. Franklin's idea was every body has around it an electrical atmosphere. And there's a natural amount of electric fluid around each body. If there's too much, we'll call it positive. If there's too little, we'll call it negative. And nature is organized so the positives and the negatives always want to balance out, like an ideal American economy.
Franklin's insight was that electricity was actually just positive charge flowing to cancel out negative charge, and he believed this simple idea could solve the mystery of the Leyden jar. As the jar is charged up, negative electrical charge is poured down the wire and into the water. If the jar rests on an insulator, a small amount builds up in the water. But if instead the jar is held by someone as it's being charged, positive electric charge is sucked up through their body from the ground to the outside of the jar, trying to cancel out the negative charge inside. But the positive and negative charges are stopped from cancelling out by the glass, which acts as an insulator. So instead, the charge just grows and grows on both sides of the glass. Then, touching the top of the jar with the other hand completes a circuit, allowing the negative charge on the inside to pass through the hand to the positive on the outside, finally cancelling it out. The movement of this charge causes a massive shock and often a spark. The modern equivalent of the Leyden jar is this, the capacitor, and it's one of the most ubiquitous of electronic components. It's found everywhere. There are a number of smaller ones scattered around on this circuit board from a computer. They help smooth out electrical surges, protecting sensitive components, even in the most modern electric circuit. Solving the mystery of the Leyden jar and recognizing lightning as merely a kind of electricity were two great successes for Franklin and the New Enlightenment movement. But the forces of trade and commerce, which helped fuel the Enlightenment, were about to throw up a new and even more perplexing electrical mystery. A completely new kind of electricity.
This is the English Channel. By the 17th and 18th centuries, a good fraction of the world's wealth flowed up this stretch of water from all corners of the British Empire and beyond, on its way to London. Spices from India, sugar from the Caribbean, wheat from America, tea from China. But of course, it wasn't just commerce.
New plant and animal specimens from all over the world came flooding into London, including one that particularly fascinated the electricians. Called the torpedo fish, it'd been the stuff of fishermen's tales. Its sting, it was said, was capable of knocking a grown man down. But as the electricians started to investigate the sting, they realized it felt strangely similar to a shock from a Leyden jar. Could its sting actually be an electric shock?
At first, many people dismissed the torpedo fish's shock as occult. Some said it was probably just the fish biting. Others that it couldn't be a shock because without a spark, it just wasn't electricity. But for most, this was a very strange and inexplicable new mystery. And it would take one of the oddest yet most brilliant characters in British science to begin to unlock the secrets of the torpedo fish.
This is the only picture in existence of the pathologically shy but exceptional Henry Cavendish. This one only exists because an artist sketched his coat as it hung on a peg, then filled in the face from memory. His family were fantastically rich. They were the Devonshires, who still own Chatsworth House in Derbyshire.
But Henry Cavendish decided to turn his back on his family's wealth and status, to live in London near his beloved Royal Society, where he could quietly pursue his passion for experimental science. When he heard about the electric torpedo fish, he was intrigued.
A friend wrote to him, "On this, my first experience of the effect of the torpedo, I exclaimed that this is certainly electricity. But how?"
And to work out how a living thing could produce electricity, he decided to make his own artificial fish.
These are his plans. 2 Leyden jars shaped like the fish, which were buried under sand. When the sand was touched, they discharged, giving a nasty shock. His model helped convince him that the real torpedo fish was electric. But it still left him with a nagging problem.
Although both the real fish and Cavendish's artificial one gave powerful electric shocks, the real fish never sparked. Cavendish was perplexed. How could it be the same kind of electricity if they didn't both do the same kinds of things?
Cavendish spent the winter of 1773 in his laboratory trying to come up with an answer. And in the spring, he had a brainwave.
Cavendish's ingenious answer was to point out a subtle distinction between the amount of electricity and its intensity. The real fish produced the same kind of electricity, it's just that it was less intense. Now, for a physicist like me, this marks a crucial turning point because it's the moment when 2 genuinely innovative scientific ideas first crop up. What Cavendish refers to as the amount of electricity, we now call electric charge. And his intensity is what we call the potential difference, or voltage.
So the Leyden jar's shock was high voltage but low charge, whereas the fish was low voltage and high charge. And it's possible to actually measure that.
Hiding at the bottom of this tank under the sand is the torpedo marmorata, and it's an electric ray. You can just see its eyes protruding from the sand. This is a fully grown female, and I'm going to try and measure the electricity it gives off with this bait. I've got this fish connected to a metal rod and hooked up to an oscilloscope to see if I can measure the voltage as it catches its prey. So here goes. Oh, there's one.
And there's another one. The fish gave a shock of about 240 volts, the same as mains electricity, but still roughly 10 times less than the Leyden jar. Well, that would have given me quite a nasty shock. And I can only try and imagine what it must have been like for scientists in the 18th century to witness this. An animal, a fish, producing its own electricity. Cavendish had shown that the torpedo fish made electricity, but he didn't know if it was the same kind of electricity as that made from an electrical machine.
Is the electrical shock that a torpedo produces, is it the same as produced by an electrical machine? Or are there two kinds? Is there a kind that's generated artificially, or is there a kind of animal electricity that only exists in living bodies? And this was a huge debate that divided opinion for several decades.
And out of that bitter debate came a new discovery. The discovery that electricity needn't be a brief shock or spark, but could actually be continuous. And the generation of continuous electricity would ultimately propel us into our modern age. But the next step in the story of electricity would come about because of a fierce personal and professional rivalry between two Italian academics.
This is Bologna University, one of the oldest in Europe. In the late 18th century, the city of Bologna was ruled from papal Rome, which meant that the university was powerful but conservative in its thinking.
It was steeped in traditional Christianity, one where God ruled earth from heaven, but that the way he ran the world was hidden from us mere mortals. We were not meant to understand him, only to serve him. And one of the university's brightest stars was the anatomist Luigi Alisio Galvani. But in a neighboring city, a rival electrician was about to take Galvani to task.
This is Pavia, only 150 miles from Bologna, but by the end of the 18th century, worlds apart politically. It was part of the Austrian Empire, which put it at the very heart of the European Enlightenment, liberal in its thinking, politically radical, and obsessed with the new science of electricity. It was also home to Alessandro Volta. Alessandro Volta couldn't have been more unlike Galvani. From an old Lombardy family, he was young, arrogant, charismatic, a real ladies' man, and he courted controversy. Unlike Galvani, he liked to show off his experiments on an international stage to any audience.
Volta's ideas were unfettered by Galvani's religious dogma. Like Benjamin Franklin and the European Enlightenment, he believed in rationality, that scientific truth, like a Greek god, would cast ignorance to the floor. Superstition was the enemy, reason was the future. Both men were fascinated by electricity, and both brought their different ways of seeing the world to bear on it.
Galvani had been attracted to the use of electricity in medical treatments. For instance, in 1759, here in Bologna, electricity was used on the muscles of a paralyzed man. One report said it was a fine sight to see the mastoid rotate the head, the biceps bend the elbow. In short, to see the force and vitality of all the motions occurring in every paralyzed muscle subjected to the stimulus. Galvani believed these kinds of examples revealed that the body worked using animal electricity, a fluid that flows from the brain through the nerves into the muscles, where it's turned into motion. And he devised a series of grisly experiments to prove it. Now, he first prepared a frog. He writes, "The frog is skinned and disemboweled, only their lower limbs are left joined together, containing just the crural nerves." Well, I've left my frog mostly intact, but I've exposed the nerves that connect to the frog's legs. Then he used Hawksby's electrical machine to generate electrostatic charge that would accumulate and travel along this arm and out through this copper wire. Then he connected the charge-carrying wire to the frog and another to the nerve just above the leg. Let's see what happens. Oh, and the frog's leg twitches just as he makes contact. There we go.
Now, for Galvani, what was going on there was that there's a strange, special kind of entity in the animal muscle, which he calls animal electricity. It's not like any other electricity. It's intrinsic to living beings.
But for Volta, animal electricity smacked of superstition and magic. It had no place in rational and enlightened science.
Volta saw the experiment completely differently to Galvani. He believed it revealed something totally new. For him, the legs weren't jumping as a result of the release of animal electricity from within them, but because of the artificial electricity from outside. The legs were merely the indicator.
They were only twitching because of the electricity from the Hawksby machine. Back in Bologna, Galvani reacted furiously to Volta's ideas. He believed Volta had crossed a fundamental line from electrical experiment into God's realm, and that was tantamount to heresy.
To have a kind of spirit like electricity, to have that produced artificially, and to say that that spirit, that living force, that agency was the same as something produced by God, that God had put into a living human body or a frog's body, that seemed sacrilegious to them because it was eliminating this boundary between God's realm of the divine and the mundane realm of the material.
Spurred on by his religious indignation, Galvani announced a new series of experimental results which would prove that Volta was wrong. During one of his experiments, he hung his frogs on an iron wire and saw something totally unexpected.
If he connected a copper wire to the wire the frog was hanging from, and then touched the other end of the copper to the nerve, it seemed to him that he could make the frog's leg twitch without any electricity at all.
Galvani came to the conclusion that it must have been something inside the frogs, even if dead, that continued for a while after death to produce some kind of electricity.
And the metal wires were somehow releasing that electricity. Over the next months, Galvani's experiments focused on isolating this animal electricity using combinations of frog and metal, Leyden jars and electrical machines.
For Galvani,
These experiments were proof that the electricity was originating within the frog itself. The frog's muscles were Leyden jars, storing up the electrical fluid and then releasing it in a burst. On the 30th of October 1786, he published his findings in a book, De Animali Electricitati, of animal electricity. Galvani was so confident of his ideas, he even sent a copy of his book to Volta. But Volta just couldn't stomach Galvani's idea of animal electricity. He thought the electricity just had to come from somewhere else. But where?
In the 1790s, here at the University of Pavia, almost certainly in this lecture theatre, which still bears his name, Volta began his search for the new source of electricity. His suspicions focused on the metals that Galvani had used to make his frog's legs twitch. His curiosity had been piqued by an odd phenomenon that he'd come across: how combinations of metals tasted. He found that if he took two different metal coins and placed them on the tip of his tongue, and then placed a silver spoon on top of both, he got a kind of tingling sensation, rather like the tingling you'd get from the discharge of a Leyden jar.
Volta concluded that he could taste electricity and that it must be coming from the contact between the different metals in the coins and spoon.
His theory flew in the face of Galvani's. The frog's leg twitched not because of its own animal electricity, but because it was reacting to the electricity from the metals.
But the electricity his coins generated was incredibly weak. How could he make it stronger? Then an idea came to him as he revisited the scientific papers from the great British scientist Henry Cavendish, and in particular his famous work on the electric torpedo fish.
He went back and took a closer look at the torpedo fish, and in particular the repeating pattern of chambers in its back. He wondered whether it was this repeating pattern that held the key to its powerful electric shock.
Perhaps each chamber was like his coins and spoon, each generating a tiny amount of electricity. And perhaps the fish's powerful shock results from the pattern of chambers repeating over and over again. With growing confidence in his new ideas, Volta decided to fight back by building his own artificial version of the torpedo fish.
So he copied the torpedo fish by repeating its pattern, but using metal. Here's what he did. He took a copper metal plate and then placed above it a piece of card soaked in dilute acid. Then above that, he took another metal and placed it on top. What he had here was exactly the same thing as Galvani's two wires. But now, Volta repeated the process. What he was doing here was building a pile of metal. In fact, his invention became known as the pile.
But it's what it could do that was the really incredible revelation.
Volta then tried his pile out on himself by getting two wires and attaching them to each end of the pile and bringing the other ends to touch his tongue. He could actually taste the electricity. This time it was more powerful than normal, and it was constant.
He'd created the first battery.
The machine was no longer an electrical and mechanical machine. It was just a purely electrical machine. So he proved that a machine imitating the fish could work, that what he called the metal or contact electricity of different metals could work. And that he regarded as his final winning move in the controversy with Galvani.
What Volta's pile showed was that you could develop all the phenomena of animal electricity without any animals being present. So, from the voltaic point of view, it seemed as if Galvani was wrong. There's nothing special about the electricity in animals. It's electricity, and it can be completely mimicked by this artificial pile.
But the biggest surprise for Volta was that the electricity it generated was continuous.
In fact, it poured out like water in a stream. And just as in a stream where the measure of the amount of water flowing is called a current, so the electricity flowing out of the pile became known as an electrical current.
"200 years after Volta, we finally understand what electricity actually is. The atoms in metals, like all atoms, have electrically charged electrons surrounding a nucleus. But in metals, the atoms share their outer electrons with each other in a unique way, which means they can move from one atom to the next. If those electrons move in the same direction at the same time, the cumulative effect is a movement of electric charge. This flow of electrons is what we call an electric current."
Within weeks of Volta publishing details of his pile, scientists were discovering something incredible about what it could do. Its effect on ordinary water was completely unexpected. The constant stream of electric charge into the water was ripping it up into its constituent parts, the gases, oxygen and hydrogen. Electricity was heralding the dawn of a new age
where electricity ceased being a mere curiosity and started being genuinely useful. With constant flowing current electricity, new chemical elements could be isolated with ease, and this laid the foundations for chemistry, physics, and modern industry. Volta's pile changed everything. The pile made Volta an international celebrity, feted by the powerful and the rich. In recognition, a fundamental measure of electricity was named in his honor, the volt. But his scientific adversary didn't fare quite so well.
Luigi Alizio Galvani died on the 4th of December 1798, depressed and in poverty. For me, though, it's not the invention of the battery that marks the crucial turning point in the story of electricity. It's what happened next. It took place in London's Royal Institution. It was a moment that marked the end of one era and the beginning of another.
It was overseen by Humphrey Davy, the first of a new generation of electricians, young, confident, and fascinated by the possibilities of continuous electrical current. So in 1808, he built the world's largest battery. It filled an entire room underneath the Royal Institution. It had over 800 individual voltaic piles attached together. It must have hissed and breathed sulphurous fumes.
In a darkened room lit by centuries-old technology, candles and oil lamps, Davy connected his battery to 2 carbon filaments and brought the tips together. The continuous flow of electricity from the battery through the filaments leapt across the gap, giving rise to a constant and blindingly bright spark. Out of the darkness came the light.
Davy's arc light truly symbolises the end of one era and the beginning of our era, the era of electricity.
But there's a truly grisly coda to this story. In 1803, Galvani's nephew, one Giovanni Aldini, came to London with a terrifying new experiment. A convicted murderer called George Forster had just been hanged in Newgate. And when the body was cut down from the gallows, it was brought directly to the lecture theatre where Aldini started his macabre work.
Using a voltaic pile, he began to apply an electric current to the dead man's body.
Then, Aldini put one electrical conductor in the dead man's anus and the other at the top of his spine. Forster's limp dead body sat bolt upright and his spine arched and twisted. For a moment, it seemed as though the dead body had been brought back to life.
It appeared as though electricity might have the power of resurrection. And this made a profound impact on a young writer called Mary Shelley.
Mary Shelley wrote one of the most powerful and enduring stories ever. Based partly here on Lake Como, Frankenstein tells the story of a scientist, a galvanist, probably based on Aldini, who brings a monster to life using electricity. And then, disgusted by his own arrogance, he abandons his creation. Just like Davy's arc lamp, this book symbolizes changing times, the end of the era of miracles and romance, and the beginning of the era of rationality, industry, and science.
And it's that new age we explore in the next programme. Because at the start of the 19th century, scientists realised that electricity was intimately connected with another of nature's mysterious forces, magnetism. And that realisation would completely transform our world.
To find out more about the story of electricity and to put your power knowledge to the test, try the Open University's interactive energy game. Go to bbc.co.uk/electricity and follow links to the Open University.
Electricity is one of nature's greatest forces. And by the middle of the 20th century, we'd harnessed it to light and power our modern world. Hundreds of years of scientific discoveries and inventions brought us here. But it would take the eccentric genius of one man to unlock the full potential of electrical power.
In the winter of 1943, Nikola Tesla looked out across the Manhattan skyline for the very last time. Tesla had been born into a world powered by steam and lit by gas. But before his eyes, he saw a new world, a world transformed, a world powered by electricity. His world. Frail, lonely, and still mourning the death of one of his beloved pigeons, this extraordinary and eccentric genius knew that his life's work was done. and he lay back on his bed to die. It would be 3 days before anyone found his body.
Just over 200 years ago, early scientists discovered electricity could be much more than simply a static charge. It could be made to flow in a continuous current. But they were about to discover something profound, that electricity is connected to magnetism. Harnessing the link between magnetism and electricity would completely transform the world and allow us to generate seemingly limitless amounts of electrical power. This is the story of how scientists and engineers unlocked the nature of electricity and then used it in an extraordinary century of innovation and invention. But not before one of the most shocking engineering rivalries in history was finally laid to rest. Our story begins in London at the beginning of the 19th century with a young man who would further our understanding of electricity as much as any other.
On the 29th of February 1812, a 20-year-old self-educated bookbinder called Michael Faraday came here to the Royal Institution of Great Britain. He was surrounded by the great and the good of the academic world, and he was about to listen to one of the greatest scientific minds of the age.
Faraday, the son of a blacksmith, had finished his formal education when he was just 12 years old. He would never get to university, but he wasn't finished with learning, as he was fascinated by science.
Faraday worked long and hard during the day binding books, but in the evenings he would read whatever scientific literature he could lay his hands on. He loved learning new things about the world, and he had this constant desire, this passion to understand why things were the way they were.
Reading scientific papers was one thing, but to really satisfy his craving for knowledge, Faraday was desperate to see the experiments themselves.
And he eventually got his chance when he was given a ticket to attend one of the last lectures of England's greatest chemist of the time, Sir Humphrey Davy. It was to change young Faraday's life forever. After watching Davy, awe-inspired and full of ideas, Faraday knew what he wanted to do with his life. He was determined to dedicate himself to furthering science.
And that's just what he did. Within a year, Davy had appointed him as an assistant at the Royal Institution.
With Davy as his patron and, well, his boss, Faraday studied all manner of chemistry.
But what would inspire his greatest breakthroughs?
With the invisible forces of electricity and magnetism.
In 1820, both were being studied by a Danish scientist, Hans Christian Ørsted, who'd made an extraordinary discovery.
He passed an electric current through a copper rod and brought it close to a magnetic compass needle and saw that it made the needle rotate. To Ørsted, it was remarkable. He'd shown for the first time that an electric current can create a magnetic force. He'd bound electricity
and magnetism together. Today, we call it electromagnetism, and it's one of the fundamental forces of nature.
Oersted's discovery sparks off a whole new spate of inventive activity around and about the fields of electricity. You can almost see electrical experimenters vying, competing with each other to find new links between electricity and the other powers of nature.
At the Royal Institution, Faraday set about recreating Oersted's work, which would mark his first steps to fame and fortune. And through his rigorous research, he concluded that there must be a flow of forces acting between the wire and the compass needle. The device he designed to demonstrate it would change the course of history. Faraday created a circuit using a battery like this, a pair of wires, and a mercury bath. Now, the circuit carries on through these copper posts, and this wire hangs freely, it dangles into the mercury. Now, because mercury is such a good conductor, it completes the circuit. When the current runs through the circuit, it generates a circular magnetic force field around the wire. Now, this interacts with the magnetism from a permanent magnet that Faraday had placed in the middle of the mercury. Together, they forced the wire to move. Faraday had proved that this invisible force really does exist, and he could see its effect: circular motion. This beautiful device was the first to convert electric current into continuous motion. Basically, it's the earliest ever electric motor. But Faraday was about to take this experiment further.
One of the lasting effects of Faraday's discovery of electromagnetic rotations in 1821 was that it showed that there was a relationship of some sort between electricity, magnetism, and motion.
Faraday explored this relationship in detail and set himself an even more difficult challenge: to use magnetism and motion to make electricity. Eventually, his obsession, hard work, and determination paid off. The breakthrough came on the 17th of October, 1831, when Faraday took a magnet like this and moved it in and out of a coil of wire. He was able to detect a tiny electric current in the coil, moving one way and then the other. Faraday knew he was onto something. A few days later, instead of moving the magnet through the conducting wire coil, he set up the equivalent experiment by moving a conducting copper plate through the magnetic field. He didn't know it at the time, but as his spinning disc cut through this magnetic field, billions of negatively charged electrons were deflected from their original circular course and began to drift towards the edge. A negative charge built up at the outer edge of the disc, leaving a positive charge at the center. And once the disc was connected to wires, the electrons flowed in a steady stream. Faraday had generated a continuous flow of electric current. Unlike a battery, his current flowed for as long as his copper disc was spun. He'd created electrical power directly from mechanical power.
Although Faraday's discovery of induction was extraordinarily important in its own right and had profound effects for the understanding of electricity and technology for the rest of the 19th century, for Faraday, what it did was to open up a decade of powerful research because it gave him the clue about how he should pursue his research.
While Faraday continued his work, trying to understand the very nature of electricity, inventors from across Europe
were less interested in the science and more interested in how electricity could make them money.
What's actually quite remarkable, certainly from a contemporary perspective, is that by and large, nobody really seems to care very much what electricity is. You don't have great theoretical debates as to whether it's a force or a fluid or a principle or a power. What they're really interested in is what electricity can do.
Faraday, living in a world of steam power, was informing the scientific community about the nature of electricity. But at the same time, another breakthrough in how we could actually use it had been made. This would be the first device that really brought electricity out of the laboratory and into the hands of ordinary people. The telegraph.
The key to understanding the telegraph is understanding a special kind of magnet, an electromagnet. Basically, a magnet created by an electric current. The first electromagnets were developed independently by William Sturgeon in Britain and Joseph Henry in America. And just as Faraday had discovered that by coiling his wire, he could increase the current in it produced by the moving magnet, so Henry and Sturgeon discovered that by adding more coils in their current-carrying wires, they could make a more concentrated magnetic field. Basically, the more coils, the more turns, the stronger the magnet. So if I pass a current through this electromagnet, you can actually see the effects of the magnetic field. This is the standard school experiment of sprinkling iron filings on top of the magnet. If I give it a tap, see the iron filings follow the contours of the field. This allows us to visualize the effects of magnetism.
To make an electromagnet even stronger, Henry and Sturgeon discovered that they could place certain kinds of metal inside the electromagnetic coil.
The reason iron is so effective is fascinating because you can think of it as being made up of lots of tiny magnets, all pointing in random directions. At the moment, this is not a magnet. The tiny magnets inside are aligned similarly to these compass needles. If you see, they're all pointing in different directions. But when you apply a magnetic field, they all align together. They all combine, these magnets, and cumulatively they add to the strength of the electromagnet. So what Henry and Sturgeon did was place 2 electromagnetic coils on each arm of their horseshoe to create something that was many, many times more powerful. And we can see the power of this horseshoe electromagnet. If I turn it on and use something slightly bigger than iron filings, these small pieces of iron, look at the strength of the magnetic field holding them in place. What's important to remember, of course, is that this electromagnet only works all the time there's a current passing through it. As soon as I turn off the current, the magnetism disappears.
Early experimenters showed off this power by lifting metal weights. Henry even made one big enough to lift 1.5 tons of metal.
Impressive, but not world-changing. But place that magnet much further away, at the end of a wire, and suddenly you can make something happen at your command, in an instant. This ability to control a magnet at a distance is one of the most useful things we've ever discovered.
If electricity can be made visible a long way away from the original source of power, then you've got a source of instantaneous communication.
By the middle of the 1840s, Samuel Morse had developed a messaging system based on how long an electrical circuit was switched on or off. A long pulse of currents for a dash, a short burst for a dot. This allowed messages to be sent and received
by using a simple code.
Contemporary early Victorian commentators reflect on the fact that electricity and the telegraph is literally making their world a smaller place. You very often get a sort of rhetoric throughout the 19th century when people are talking about the telegraph about how more communication, more understanding will render war obsolete because we'll all understand each other better. I mean, retrospectively, it seems hopelessly utopian.
By the 1850s, Europe and America were crisscrossed with land-based telegraph wires. But the dream of instant global communication was frustratingly out of reach. This was because there was still no cable capable of carrying messages between two of the greatest powers on Earth, Britain and America.
Many experts were convinced that a working Atlantic cable was impossible. But those who disagreed knew that if they could solve this problem, it could make them serious money. And in the 1850s, American businessmen and British engineers joined forces to prove this could be done.
Attempt after attempt ended in disaster. The heavy cables kept snapping in heavy seas and storms.
Finally, on the 29th of July, 1858, two parts of a cable were spliced together in mid-Atlantic. You see, a single cable was simply too big to have been carried by one ship. Then one end was taken to Newfoundland and the other end to Southwest Ireland. 6 days later, the first direct link between the two most powerful nations in the world was in place.
The project was hailed a huge success, and a formal message of congratulations was sent from Queen Victoria to President Buchanan. But before the celebrations were over, things started to go very wrong. This is Chief Engineer Bright's original notebook. You can see here Queen Victoria's original message. Now, it's only 98 words long, but it took 16 hours to transmit. The telegraph operators on the other side found it very hard to decipher the message. The electrical signals that they were receiving were blurred and distorted, and they kept asking for words to be repeated over and over again. So you can see here, repeat after sending, waiting to receive, no signals. Clearly, transmitting across the Atlantic wasn't going to be as straightforward as people had hoped. Over the next few days, several hundred messages were exchanged. But those arriving in Newfoundland became almost impossible to decipher. Just a jumbled mess of dots and dashes. There was a serious problem with the cable, and it was getting worse. Well, the 1858 cable was never fully repaired, and the end finally came when British engineer Wildman Whitehouse mistakenly believed that by increasing the signal voltage, he could force the messages through to Newfoundland. The cable simply stopped working altogether. At the time, increasing the voltage by using more powerful batteries made sense. Most experts believed electric current flowed through a cable like a fluid in a pipe. Increasing the voltage was the equivalent of increasing the pressure in the system, forcing the current through to the other end. But the telegraph was actually carrying pulses or ripples of current along the cable, not a continuous stream. And over long distances, these pulses were becoming distorted, making it difficult to tell what was a short dot and which was a longer dash. By studying the effectiveness of underwater cabling, scientists were beginning to understand that electric current didn't always flow like water, but was also creating invisible electromagnetic waves or ripples. And it's this breakthrough that would lead to a new branch of research into the electromagnetic spectrum and solve the problems of the Atlantic telegraph.
In effect, the transatlantic cable was a giant, ambitious, hugely expensive experiment. The failure of science to keep pace with technology had been exposed, and a new, more theoretical, and for me, much more exciting approach to understanding electricity began to unfold. Armed with this new understanding of how electric pulses actually moved along the cable, improvements were made to its composition, design, and how it was laid. It would take another 8 years of scientists and engineers working together before a working cable was finally put in place. And on Friday, the 27th of July, 1866, a message was sent from Ireland to Newfoundland, clear and crisp. A treaty of peace has been signed between Austria and Prussia. At last, the dream of instant transatlantic communication had become a reality.
The success of the 1866 cable makes the world a smaller place, yet again. The change from a world where it took days or weeks or months for information to travel to a world in which information took seconds or minutes to travel is far more profound, I think, than anything that's taken place during my lifetime.
The invention of the telegraph changed ordinary people's lives. But it would be the breakthroughs in how we used continuously flowing electric currents that would have an even greater impact. Because inventors were developing a new way of using electricity. To make something every person in the world would want. Electric light. Until the 19th century, we only knew of one way to make our own light: burn things. And by the middle of the 19th century, we'd perfected a very effective way of lighting our homes, using gas. A typical British home in the 1860s would have been lit like this. Highly flammable gas would have been pumped directly into people's houses through a network of pipes. But these gas lamps were too dull for large outdoor areas. So railway stations and streets began to be lit from a more powerful source: electric arc lights. The first arc lights were demonstrated by Michael Faraday's mentor, Sir Humphrey Davy, at the Royal Institution as early as 1808. And they worked by passing a continuous spark of electricity across 2 carbon rods. But their intense white glow was just too bright for people's homes. For an electric light to compete with gas, it would need to be subdivided into many smaller, less powerful and more gentle lamps. Whoever succeeded in bringing electric light to every home in the land was guaranteed fame and fortune. And by the early 1880s, the most famous, most prodigious, most fiercely competitive inventor in the world had taken on the challenge: the American Thomas Alva Edison.
For Edison, invention was a passion. It's what he loved doing. He loved being in the laboratory. The first thing that drove that passion is that it was a lot of fun for Edison. I think that was the thing that he found most exciting, is that this was something he did well, and it allowed all of his creativity to come to the fore.
Edison is Mr. Electrical Invention. He's the man they trust. He's the man that they think can do anything. He's also the man who has his carefully cultivated connections with entrepreneurs, with people who are willing to put their cash where Edison's mouth is, so to speak, and back him in this sort of venture.
For Edison, the money was probably the least important reason. For Edison, the money was important for one reason: to allow him to do the next project.
Edison had assembled a group of young and talented engineers at a cutting-edge laboratory in New Jersey, 26 miles from Manhattan. Menlo Park would become the world's first research and development facility, allowing Edison's team to invent on an industrial scale.
They worked incredible hours. One of them talked about how he hardly ever saw his children because he was in the lab all the time. But they knew they were in the midst of something really important, right? That if Edison succeeded, right, if they succeeded with Edison, that their futures were secure.
Edison's dream was to bring electric light to every home in the land. And with his team of engineers behind him and the vision of an electric future ahead, he launched his campaign.
The race to bring electric light to the world was to play out in the great cities of the time: New York, Paris, London.
Edison's Menlo Park team set about developing a totally different form of electric lamp, the incandescent light bulb. In fact, Edison's light bulb design wasn't all that new or unique. French, Russian, Belgian and British inventors had been perfecting similar bulbs for over 40 years. And one of them, an Englishman, Joseph Swan, had been developing his own version of an incandescent lamp. Both Swan and Edison's light bulbs work by passing an electric current through a filament. Now, a filament is a material in which the electric current flows through with more difficulty than it does through the copper wire in the rest of the circuit. And it relies on the idea of resistance. Now, inside this jar, I have a filament made out of ordinary pencil lead, and we can see what happens as I pass a current through it. Down at the atomic scale, the atoms in the filament impede the flow of electricity, so it takes more energy to force it through, and this energy is deposited in the filament as heat. Now, as it heats up, its resistance goes up, which again raises its temperature until it glows white hot. Now, one of the first materials Edison used for his filaments was platinum. With its relatively high melting point, platinum could be heated to a white-hot temperature without melting. It could also be stretched into thin strands, and the thinner the strand, the more resistance it offered to the current passing through it. But platinum was expensive and didn't offer enough resistance. The race was on to find a better alternative. And the solution came when the Menlo Park team switched to a method Swan was also developing, using a vacuum to stop cheaper carbon filaments from burning up too quickly. Edison and Swan tested all kinds of different materials for their filaments, everything from raw silk and parchment to cork. Edison even tested his engineer's beard hair. Eventually, he settled on bamboo fiber, while Swan used a treated cotton thread. Edison and Swan's light bulb designs were very similar. Eventually, they came to an agreement and went into partnership to sell light bulbs in the UK. Today, many people still believe that Edison alone invented the light bulb, while Swan has become a footnote in history. But his incandescent bulb was only part of Edison's strategy. He'd also invented an entire electrical system of sockets, cables and meters to go with it. And being a brilliant businessman, he'd developed a groundbreaking new way of distributing electricity. Edison knew that the key to making money from his system was to generate the electricity in a central station and then sell it to as many customers as possible. It seems obvious to us now, but until then, anyone who wanted to use electricity had to have their own noisy generator to make it. Edison's ambition was huge. He wanted to light the fastest growing and most exciting city in the world. New York.
In the summer of 1882, Edison stood in a unique position at the center of 19th century science and invention. He'd patented a cutting-edge incandescent light bulb. He'd amassed an unprecedented knowledge of electrical engineering. And above all, he'd cultivated a reputation among the American public of being such a genius inventor that journalists hung on his every word. And the financial muscle of Wall Street was quick to throw itself behind his new ideas. His vision to electrify Manhattan, and then of course the rest of the world, was seemingly within his grasp.
Because Edison and his team were about to launch their most expensive and risky project yet. America's first power station generating continuous direct current.
Just before 3 p.m. on the 4th of September 1882, Thomas Edison, surrounded by a gaggle of bankers, dignitaries and reporters, entered J.P. Morgan's building right behind me, flicked one of the Edison patented switches, and 100 of his incandescent bulbs began to glow. Turning to a nearby journalist, he said, "I have accomplished all that I've promised."
Half a mile away on Pearl Street, Edison's new power station, costing $500,000 and 4 years of hard work, had sprung into life. The current surged through buried cables, stretching out in each direction.
Of course, it might seem obvious to us now, but in New York back in the early 1880s, the idea of burying electric cables underground seemed like an unnecessary expense. This street would have been crisscrossed with hundreds of cables used for telegraphs, telephones, and arc street lighting. Looking up, you'd have seen a tangled mass of black spaghetti blocking out the light.
Edison knew this dangerous situation had to change, and for him to make as much money as he could, electricity needed rebranding. It had to be considered safe.
So Edison is arguing both for the greater safety of his DC low voltage system and for underground lines. He can argue that he has a much safer system than electric arc light for streets or gas lighting for indoor lighting, right? He doesn't have to worry about fires, doesn't have to worry about electrocution, that all of this is much safer because of the system he's created with this underground system.
Burying every cable was not only very expensive, but was a logistical nightmare, because this was one of the busiest square miles in the world.
Edison chose this area for a reason. Wall Street. Rich, important, influential. Because for Edison's system to make money, all these wealthy customers had to be within a mile of his power station.
And this was because Edison calculated the thickest cable he could afford would only carry an adequate amount of his continuous direct current to customers within this range. This was a huge leap forward, because for the first time, dozens of customers could be supplied by just one power station. But there was a big problem. Edison's network could never be economical in lighting America's new suburbs.
They just didn't have the concentration of customers needed to make building these expensive power stations worthwhile. Had we stuck with Edison's way of generating and distributing electricity, the world would be a very different place. We'd have to have power stations scattered around no more than a mile apart, even in the centres of our towns and cities. And it would be extraordinarily expensive to even provide power for smaller communities. But someone who held the answers to these problems was about to enter the story. Someone who would help create the modern world and who'd play an integral part in one of the biggest fallouts in scientific history. His name was Nikola Tesla, and he was right under Edison's nose. Nikola Tesla was a Serbian inventor who was born in Croatia and who worked for Edison briefly after arriving in New York at the age of 28. European, introverted, a deep thinker. He was everything Edison wasn't.
Edison and Tesla could not be more different in the way that they handled their self-appearance and their manners, and the way that they constructed a public image for themselves. Edison could care less about the clothes that he had on, and if he spilled chemicals on his good Sunday suit, then he spilled chemicals on his good Sunday suit. He was, basically a very, very kind of slovenly guy. Tesla, on the other hand, even as a young man in his mid-20s, is thinking about his appearance, how he comes across to people, so he cares about his clothes, he cares about his manner, indeed he even cares about how his portraits are taken, and he always wants to make sure that he has a nice three-quarter profile, so you don't see the fact that he has a bit of a pointy chin.
The life and death of Nikola Tesla is one of the most fascinating yet tragic stories of scientific brilliance, cutthroat business, and shocking public relations stunts. The American public may have been wowed by Edison's new direct current power stations, but Tesla was less impressed. He had a dream electricity could be transmitted across entire cities, or even nations. And he believed he knew how it could be done, by using a different type of electric current. Electrical experts knew that the smaller the current sent down a cable, the smaller the losses in it through resistance, and so the longer the cable could be. Tesla proposed using a method of transmitting electricity where the currents could be lowered without a fall in the amount of electrical power at the other end. It was called alternating current. Alternating current is exactly that. It's an electric current that alternates between moving in one direction, then the opposite direction very quickly, as opposed to a direct current which moves only in one direction.
Tesla was interested in alternating current because, like other electrical engineers in the late 1880s, he realized that as you raise the voltage of any current that you transmit from point A to point B, it's going to be more efficient to have a higher voltage.
And since the amount of electric power in a cable is its voltage multiplied by its current, increasing the voltage meant the current in the cables could be reduced, and so losses due to resistance would be less.
However, you don't want very high voltages on the order of, say, 20,000 volts coming into your home. So you need to step down the current that is being transmitted over a distance into your home, and to do that you need a converter or a transformer. Alternating current allows you to use a transformer to make that switch from the high transmission voltage to the lower voltage that you're going to use at consumption.
Perfecting the technology to transmit electricity hundreds of miles from where it was generated would mark a huge step towards the modern world. And a wealthy industrial entrepreneur was already developing the solution. His name was George Westinghouse. Westinghouse believed alternating currents was the future, but it had a big drawback. While it was